Solving inequalities. We've already covered solving linear inequalities, and that's where you don't have any exponent no exponents on the variables. Sort of like a linear equation, except in this case it's a linear inequality. It's pretty straightforward to solve this problem. You simply get all the x's on one side, the numbers on the other. So in this case, maybe I'll subtract 2x from both sides, and I'll subtract 3 from both sides, then divide both sides by 4. Now, if I want to turn this around, I would say x is less than or equal to -1. And then I could graph the number line and write the answer as an interval, go from there. However, now we're going to do something different, where we're going to look at not linear equations, but quadratic and other kinds of inequalities. But first, when I looked over the homework, before we get to this, which is the main part, they have some questions on if we're given graphs, how to solve inequalities when looking at a graph of a function. So just by hand, I've drawn up a graph of a function. This is not real complicated, but let's talk about this first before we do the math part. So here is graph of a function. You notice the horizontal axis is of course labeled x, the up and down is y. Of course y is the same thing as f of x. This is really my function. So this is the graph of my function, and here are the values of x. So here's the typical kind of question they ask. They might say that solve f of x greater than 0. What they're really saying here is go find the values of x, and it's going to be an interval. Go find the values of x where the function is greater than 0, or in this case, greater than 0 means positive. So go look at this graph and see where the function's positive. Of course, the function is like the y. The function is what's going on up and down. So in other words, if I look at when x is -2, the function is 0, because that's what y is. If I look here, say when y is -1, when x is -1, I would say my function is also -1. Maybe when x equals 1, my function is 1. So the function is the up and down, the y of this graph. So the question is, where is the function positive? That means, where is the graph above the x-axis? And looking at this graph, where is y positive? Which is what f of x, where's f of x positive? Well, it looks like there's 2. Here, the function's positive, and then the function goes negative and stays negative until you get to here again, and then it goes positive. So it looks like there are two regions of this graph where the function is positive. So the solution is, what are the values of x where the function is positive? I've got two regions here, so I'm going to union them together. Of course, you've got the arrow here, so this thing actually goes on forever. So this first region where the function is positive starts at negative infinity and goes all the way to -2. And you notice I'm not going to include the -2 because I'm asking where is the function positive. If it had been greater than or equal to 0, I would have included the -2. But because I was looking for greater than 0, excuse me, I do not include the -2. So this, I can think of like the first region where the function is positive. This is the second region where the function is positive. So I'm going to union it. It goes positive when x is 0, and it stays positive until x gets to 2. So this is the solution to the question of where is the function positive. Just for fun, what if they then said, solve this one, where is the function negative? When I'm looking for the places where the graph is below the x-axis, because that's where the function or the value of y is negative. Once again, it looks like I have two regions. The first one is here. It looks like it starts at -2 and goes to 0, and then it gets unioned. So it's positive, and then back here at 2 is when the function goes negative again. And then it goes on to infinity. All right, so if you're given the graph of a function, and then you're asked to solve some kind of inequality, it's not too difficult. I think I made up one more graph. Let's look at this one. So here we have some asymptotes. My graph isn't great. This should be typically more curved. But you get the idea. So here we have some asymptotes. I have a couple of vertical asymptotes. In other words, you can see that the looks like it maybe -2 and 1. I have asymptotes. So the graph never touches or crosses these asymptotes. It also looks like I have a horizontal asymptote when x is 0, because you can see the graph when I head in the negative x direction or the positive x. Once again, it sort of gets close to the axis but never crosses it. So the same kind of question. Here's what they want me to solve. Let's do the same thing. They want to know where the function's positive. So once again, the question is, where is the graph positive? Where is it? Greater than 0. Now once again, it's not clear here, but actually the center of this graph, it touches the x-axis, and I would say if this is 0 and -1, looks like it touches it at about -0.5. So hard to see, but this graph does actually touch the x-axis, and that's going to become important in a minute, and we'll see why in a minute. So let's see, where is the function positive? Obviously it starts out positive, and then it decreases, but it's still positive. But when it gets to here, it actually touches the x-axis. So at the point at which it touches the x-axis, it's not positive anymore, it's 0. But then it turns around and becomes positive again and goes up. And then you notice this piece over here, this thing's positive the whole time. Of course, over here, the function's negative. So there are two parts where it's positive, but be careful, but because this graph touches the x-axis, it adds one complicating factor. As a matter of fact, I really need to break this up into three regions. The first region is the left half of this, because I have to stop. I cannot include the point here where the graph touches the x-axis, but I pick it up again over here. So if I say that point x there is like negative 1/2, the solution to this would be negative 2 is where my asymptote is, and I go to negative 1/2. I cannot include the negative 1/2 because at negative 1/2 the function is 0, and I'm looking for the function is positive. And then I union it. I start at negative 1/2 and go up. This is 1 right here. X is 1. So that's sort of the right side of this graph here. And then there's one more positive region. It starts at 1 and goes to infinity. So there are actually three regions. Now it's interesting. What if they had asked for where's the function greater than or equal to 0? Well, now, because the solution includes when the function's 0, this whole part of this graph is all the solution. So I don't have to break it up, because even though it's 0 right here, that's part of my solution. So I can say negative 2 to 1 union with 1 to infinity. Hopefully you all see the difference here. And then just to finish this out, if they say, okay, where's the function negative? There's only one part of the graph where it's negative. And it starts at negative infinity and goes up to negative 2. So if you ever ask to solve an inequality where you're given the graph, it's pretty simple. It's the easiest kind of problem you're going to get, actually, with solving these inequalities. Because now we're going to go back and start looking at solving inequalities, not given a graph, but given an expression. And there can be a fair amount of work involved in solving these kinds of problems. So let me go back to where we started. So we just took a quick look at graphs. They're not too hard. But now we're going to look at inequalities. So for instance, here's a very typical kind of problem you'll be given. X squared minus 3x minus 40 less than or equal to 0. Solve them for x. In other words, figure out the values of x that's going to make this thing true. Now, just to compare up here, I had this kind of problem, but because it was a linear inequality, I could get x by itself on one side and I'm done. But here, because this is like a quadratic expression, x squared minus 3x minus 40, I can't just get x by itself on one side. I'm not able to do that. So in this case, let me write down the steps that I go through when I solve this kind of problem. And this is actually different than I think what the book does. But once again, the way I do it, I think to me is easiest to understand, and it's pretty clear, hopefully, how to do it, and you get the correct answer, of course, when you do it this way. First thing you have to do, and if you can't do this, and you probably cannot solve the problem, you have to be able to factor. So here's our trinomial that does factor. The product here is going to be negative 8. The factors are negative 8 and 5, because when you multiply negative 8 and 5, you get minus 40. But when you add negative 8 and 5, you get minus 3. So since these are the factors, I can factor this expression into this. Now, just want to make a note here. When we get to the end of this problem, when we get the solution, I'm going to make note of this. But you know what I'm looking for? Here's what this problem is about. I'm looking for the values of x that cause this expression to be less than or equal to 0, which basically means I'm looking for the values of x that cause this left-hand side to either be a negative number or it can be 0. And it's going to be an interval. It's not just going to be one number for x that makes this true. It's going to be an interval, and maybe a couple intervals that we have to union together. I don't know. We have to go solve it. So the first step is factoring. The second step is to find the zeros. The zeros of this expression are the values of x that would cause the whole expression to equal 0. That's why they're called zeros. In other words, if I look at this first parenthesis, what value of x would cause this first parenthesis to be 0? And since you have 0 times a parenthesis, it would therefore cause the whole left-hand side to be 0. Well, obviously, if x equals 8, this parenthesis 0, the whole thing is 0. If I look at the second parenthesis, if x is negative 5, then once again the whole expression would be 0. So these are called the zeros of this expression. Now, I'm going to go sort of make a little graph. And I'm going to mark these zeros, and I'm going to use these zeros to break my graph up into regions. So this is all going to be sort of new. So this is like my x-axis. So like here's 8, maybe here's negative 5. I am now, I sort of put these dashed lines, I'm now breaking up my x values into 3 regions. I'm going to label it region 1, region 2, region 3. As a matter of fact, if you think about it, out here is where x is negative infinity. Out here is when x is infinity. So I have 3 regions. The first region is when x goes from negative infinity to negative 5. The second region is when x goes from negative 5 to 8. And the third region is when x goes from 8 to infinity. Now the reason we break up into regions is because here's what happens with this expression. In each of these regions, no matter what value of x I choose from this region, and if I plug any value of x from this region into my original expression or into the factored expression, either one of these, whatever number I choose from region 1, when I plug it in here, this expression is always going to give me the same sign. It's either always going to be a positive number or always a negative number. In other words, if I chose minus 10 and I plugged in minus 10 for x, Now at this point, I don't know whether it gives me a positive or negative number. All I know is every time I choose an X from region 1 and I plug it in here, it's always going to give me the same sign. And then if I go to region 2 is when X is between -5 and 8. So if I choose -3, and I choose 0, and I choose 2, and I choose 7, all those values of X are in the second region. If I plug in all of those values into my expression, it's going to always be positive or always negative. Once again, at this point, I don't know which it is, but it's going to all be the same. And that's the same thing in region 3. So the goal is, what I want to do is, I need to find out for each of these regions if it's a positive or negative region. I need to figure out for region 1, all the X's in region 1, does it give me a positive or negative result when I plug them into my expression? I need to go to region 2 and figure out when I take a number, when I take a value of X from region 2 and plug it into the expression, is it positive or negative? So that's really the goal for the rest of the problem. As soon as we determine whether the regions are positive or negative, then we're basically done and we've solved the problem. And you'll see that in a minute. So how do I determine whether each region is positive or negative? You do this thing called you create a sign chart, which maybe some of you have done. Now once again, everything I'm doing here, I'm pretty sure is not in the book. But this to me is a way that's understandable and it works and it makes sense to me. So here's the sign chart. We're going to create a bunch of columns. The first one I call region. Turns out, from looking at my graph, I have 3 regions. The second column I'm going to call test point. So what you do is you go into each region and you choose a value of X inside that region. Don't choose what I call like the border point or this boundary point. You got to choose it actually in the region. So region 1, I'll choose -6. Region 2, if I go from -5 to 8, 0 is in here someplace. 0 makes the math easy, so I'll choose 0 for region 2. Region 3, I need to pick some value larger than 8. I'll just choose 10. Now, the next column, I go back to my factored expression and I write down each factor one at a time. Right? Factors are things you multiply. So this parenthesis is a factor, this parenthesis is a factor. So I write down my first factor, and then I write down the second factor, and then the last column, you'll see in a minute why I call it overall. So here's how a sign chart works. Region 1, I'm going to use -6 as my test point. What I'm actually doing is I'm going to set X equal to -6. So I look at this first column. Since X is going to be -6, if I plug in -6 in for X, this whole thing equals -14. And what I want to mark here is just the sign. Is it positive or negative? Well, when -6 gets plugged in here, this thing equals -14, it's negative. When -6 gets plugged in here, -6 plus 5 is -1, it's negative. And the overall is you multiply together, in this case, these two signs. What's a negative times a negative? It's a positive. So here's what I've just discovered. I've just discovered that region 1 is a positive region. I even go up here and I put a positive sign. What does that mean? Here's what that means. If I choose any value of X that's between negative infinity and negative 5. So I can choose negative 20, negative 15, negative 8, negative 6. Any of those numbers, if I plug them in to this expression, the whole expression will be a positive number. That's what it means when I stick the positive here. Region 1 is a positive region. Any value of x I choose in region 1, the expression is going to end up being positive. Let's go find out about region 2. Region 2, my test point is 0. I plug in 0 into here. 0 minus 8 is negative 8. I think I get a negative here. If I plug in 0 here, 0 plus 5 is positive. And now the overall is a negative times a positive. I have just now determined that region 2 is a negative region, which means any value of x I choose between negative 5 and 8. So I can choose negative 6, negative 3, 0, 1, 5, 6, 7. All those values of x, when I plug them in to my expression, will give me a negative result. So I say it's a negative region. And finally, region 3, my last region, my test point's 10. I plug 10 into here. 10 minus 8 is 2, so that's positive. 10 plus 5 is 15, that's positive. You multiply two positives, you get a positive. Region 3 is a positive region, which means any value of x greater than 8, if I plug it in here, this expression is going to be positive. Now, I said a few minutes ago, once we figure out the signs of the regions, we're pretty much done. Why did I say that? Because, what am I looking for here? The initial problem is saying for what values of x is this expression less than or equal to 0? I'm looking for the values of x that cause this expression to be negative. What am I looking for? I'm looking for the negative regions of my graph. In this case, I have one region that's negative. So these are the values of x that will give me a negative result. So the solution is this interval from negative 5 to 8. In other words, any value of x that I would choose between negative 5 and 8, if I would plug that value of x into my original expression, the whole thing would be negative or less than 0. So this is my solution. So what I'm going to do is I will stop this video and we'll pick up and we'll do one or two more examples of how to solve these kinds of inequalities.